This is a statistics class, so of course we have to go over probability, right? And probability gets really complicated really fast. And this class does some of the complicated things. A lot of the complicated things we don't do. So honestly, I'm just kind of following the curriculum for this. So let me just show you some things that we were doing for probability. We talked about the idea of a probability distribution. It's basically a chart that gives all the things that can happen and then like list the probabilities of each of those things. And in order for something to be a probability distribution, all the probabilities have to be between 0 and 1. Like you can't have a negative probability. And also the sum of all the probabilities has to equal 1. Okay. Now, after we talked about that, we talked about like combining probabilities. So finding the probability of like one thing or another thing happening, or the probability of not something happening. And to do this, we had to review this idea of the word mutually exclusive. Does anyone remember what mutually exclusive means? No? Can happen at the same time, right? So for example, me being in this room and me being in the room next door, those two things can't happen at the same time. Those things are mutually exclusive. Now, there's 3 probability rules. The first rule has to do with things that aren't mutually exclusive. And I told you that we're not really doing this rule. It's not in the curriculum, not on the final exam. So we're not going to be using this formula at all in this class. But there's basically 2 other rules that we have to know. If we have mutually exclusive events, meaning they can't happen at the same time, if I want to find the probability of one thing or the other thing happening, you just add together the probabilities. It's really easy. You just add together whatever you're interested in, okay? And then we had the third rule that had this weird symbol, AC. We read it as a complement. And what that means is it's just the opposite of whatever we're interested in. If we want to find the probability of the opposite thing happening, we take the number 1 and subtract the probability of the other thing happening, okay? So the rules look weird, but once you put into practice, it's pretty easy, okay? We did example 4 where we took a bunch of different things, which were the exact number of people who have high blood pressure. We have a probability distribution, and we said that all of these individual events are mutually exclusive. So these are the formulas that we're used to, okay? If I want to find the probability of like 2 or 3 or 4, it's really easy. You just add together the probabilities that you're interested in, right? Then we talked about the complement rule, which said, if I wanted to find the probability of something not happening, well, just take the probability of it actually happening and subtract it from 1. Okay, so basically 2 rules that we use: either add together the things that you're interested in or subtract the thing you're not interested in by 1. Okay, let's come up to the front here. Very nice job as I've been walking around. This has been a while since Monday, so kind of surprised you guys clung on to this so well. All right, part E, I wanted to find the probability of getting a 3 or more. And let me just erase what I have here so I can point to stuff easier. This one was Courtney. Do you want to take us through this one? Perfect, right? Just find 3, find everything more than 3, and add them together. Nice job there. Then part F wanted me to find the probability of not being 2, and that was Claudia. Sorry, I completely lost my brain there.
So I just did the opposite, like of it being 2, so I did 1 minus the probability.
Perfect, right? So getting that gets our answer of 0.73. Did anyone do a different method for number F? Okay. Just saying there's another way to do part F, right? So I know that everything that's not 2 is 0, 1, 3, and 4. So another way you could have went about part F is added 0.23, 0.41, 0.08, and 0.01. You'd still get 0.73. It's just an alternate way to do this. I do think the way that Claudia did her answer is probably the easiest method. So nice job there. Any question on part E or F? Sounds good. All right. One last thing I want to talk about with probability are probability distributions. So there's actually a way to graph probabilities by just sticking it in something that looks like a mix between a bar graph and a histogram, okay? So let's see what we have here. over here, I have a probability distribution. It looks a little bit different than what you're used to because the rows are like vertical instead of horizontal. But basically I have everything that I'm interested in, and then each value is listed with their probabilities, okay? We can turn this into a histogram by just putting all the X values on the X-axis, and the bars go as high as the probabilities are. So that's basically what a probability histogram is. Just shows everything that can happen in their probabilities. Okay, here we have a probability histogram for the number of children a person has. I'm going to change this to the exact number of children. So for example, it shows like the probability of having exactly 3 children is 0.154, for example. Okay. Can these things happen at the same time? Can you have exactly 4 and exactly 8 children at the same time? No, right? So if they can't happen at the same time, are we mutually exclusive? Yes, right? It's kind of like the opposite of what you think. These things are mutually exclusive. Right. So let's take a look at these questions. For part A, if I want to find the probability that a randomly chosen person has exactly 2 children, it's really easy. All you have to do is look at the bar labeled 2, and the probability is 0.244. So it basically is a probability distribution, but you read it as a bar graph. Yeah.
Would we be marked off and looking at as percent?
Okay, so I would say for the homework and for the online tests, yes. For some reason, our textbook just doesn't like percentages. If it was on a quiz or something, totally fine. But our textbook like hates percentages when we deal with probability. So I will say, like, let's just stay away from percentages. But it's fine with me. There's really nothing wrong with using percentages. All right. Now I feel pretty confident. Why don't you try doing B, C, and D, and we'll come back in. Right, let's come back up to the front here. So we have a couple more probability questions here. Part B wanted to know the probability of fewer than 2 children. Rylan, you wrote this one up, right? Do you want to take us through it?
I just took all the numbers that were lower than 2, added them together, and got 0.43.
Perfect, right? So just all the numbers that are lower than 2, and we got our answer there. Part C wanted to find either 4 or 5. This one was, yeah, was that Niara? Do you want to take us through your answer?
I just took the numbers of 4 and 5.
Perfect. And then finally, I wanted to find any event except someone having exactly 3 children. Alyssa, do you want to take us through this one? Perfect, right? So using the complement rule there, very nice. Any questions on finding combinations of probabilities? It's really not that bad, right? You add them together or you subtract from one. Pretty much it. All right, I guess that means we can start a brand new section. I'm actually mixing together sections of the textbook here. Technically, we're in chapter 6.1, but I mixed it together with other sections that I supposed to cover. So brand new set of guidance anyway. Oh, I'm sorry, Hannah. It's like you're not in the classroom. Oh my goodness. Wow. Me disregarding the SI in the room. Wow. Amazing. All right. Okay. So here we're going to look at a new set of guided notes. We're going to continue with probability distributions. And then we're going to kind of branch off to working with those and combining together those numbers. So I actually haven't done any work with having you create a probability distribution. And it's pretty easy. I don't know if I'm going overkill with these examples here, but let's just go over something. Okay. let's say I have a die and the die is loaded in some sort of way. Does anyone know what a loaded die is? What is it?
Not even, it's like you put a weight on one side so it will come like that out.
Yeah, it's like a die where there's like a weight on one side, so it's more probable to get some numbers than others. Usually a die has like equal probabilities for every single number, but casinos usually use loaded dies to like make people lose because, well, some numbers are going to be more probable than other numbers getting rolled. It's actually kind of interesting how casinos do this. They do a lot of stuff to make people lose games, which is why you probably always lose money at a casino unless you're really good at it. Okay, but anyway, this die is loaded in a way where all the probabilities of the numbers are like a half, a 6, a 12, and so on. Okay. Now, if I were to make a probability distribution, remember that X represents all the things that can happen. So in this case, X is just going to be all the numbers you can roll, right? Okay. And then underneath each of the numbers are going to be each of their probabilities. So in this case, it's really easy. It's just a half goes with 1, a 6 goes with 2, and then all the rest of them gets 1 out of 12. Okay, so sometimes creating a probability distribution is really easy. You just have to list all the things that are possible and then each of their probabilities. Not too bad, right? Sometimes it's a little bit more hard, okay? This time we have a box, and inside this box, we have 3 $1 bills, 2 $5 bills, 1 $10 bill, and 1 $20 bill. Now, usually the question will tell you what X or the variable represents. And this time it says X is the value of the bills. Okay, so we have X values, we have probability values. We have 2 different types of numbers getting thrown around here. What do you think is going to be in the X row? The values, right? I know there's like 3, 2, 1, and 1, and then there's a 1, 5, 10, and 20. The number that goes in the X values are the actual values of the bill. So like a $1 bill, or a $5 bill, or a $10 bill, or a $20 bill. Okay, so these are the actual things that can happen. Underneath them are the probabilities. Now this one's a little bit harder than example 1 because, well, they don't give you the probabilities. But one thing I like to do when I find the probabilities of things is usually I like to find the total number of things first. How would I find the total number of things that I'm interested in? Add them up, right? So I have 3 $1 bills, 2 $5 bills, 1 $10 bill, 1 $20. I guess I just have to add together the 3, the 2, the 1, and the 1. Okay, so if you do that, you get 7. In this class, whenever we deal with probability, we're doing parts out of a whole. So if the total amount of things that can happen is 7, that's got to be the denominator or the bottom of the fraction for each of the probabilities, right? And once you have that total, it's going to be really easy to figure out what goes on top because you have 3 of the $1 bills, 2 of the $5 bills, 1 of the 10s, and then 1 of the 20s. So it's a little bit harder when it doesn't tell you exactly what the probabilities are, but honestly, it's not too bad once you set up the chart. Okay. Any questions on these examples? Not too bad. All right. So we have a probability distribution. I guess what is coming up is, well, finding the mean of it, right? We've done the mean of a list of numbers and the variance of a list of numbers, but now we have numbers that have different probabilities or weights for each of these numbers, which means the mean is going to be different than just adding them up and dividing by how many, okay? Now, before I talk about the mean of a random variable, let's do some review. Okay, we talked about the mean of things, in particular the population mean. Okay, does anyone remember the symbol we use for the population mean? That's the sample mean. It's actually mu, right? The sample mean is X bar. It's been a while. And then the population mean is mu. Oh my, I'm getting mixed up now. Okay, but mu is the population mean. Okay, I like to think, I like to remember this as the population symbols always are Greek letters, and then the sample symbols are usually like actual letters. But the population mean is mu. Okay, now, if I'm dealing with a random variable, which just means I'm dealing with probabilities. So I'm given like a chart with all the probabilities. When we talk about the mean of random variable, we're still going to use mu, but because we're dealing with probability, to set this apart from the regular mean, we're going to put a little x at the bottom. Okay, so usually a random variable uses the letter x. So we're just going to put mu sub x, mu subscript x, to say we're taking the mean, but we're dealing with probabilities. Okay, I'm going to give you a formula for this. Honestly, I hate formulas. I don't like using them. I think memorizing them is kind of dumb. I have a different way of finding the mean, but if you're good with formulas, go ahead and memorize this, okay? I'm going to write out this formula. Uppercase sigma in brackets x times p of x. Okay. Now, so I'm going to say memorize this if you want to, but I'll show you how to use this formula, and it might be easier to just memorize how to use it instead of what the formula says. Okay, so it's saying the mean is equal to, in brackets, this x value just represents all the things that can happen, right? So basically this is saying, take all the things that can happen, multiply them by their probabilities, and then does anyone remember what this uppercase sigma symbol means? Take the sum, right? So basically it's telling us, take our x values, multiply the probabilities, and then add up all the numbers that you get. Okay, let's do an example. I think the example will show you an easier way how to do this instead of just memorizing what the formula says. In this example, we have a computer monitor. In every computer monitor, it's actually composed of all these things called pixels, which are just like the little lights that can have different colors that create the screen. They're really tiny, so usually there's a couple defective pixels in a computer screen. You usually just can't tell because they're so small. So basically what we have is a probability distribution where we have the probability of getting 0, 1, 2, or 3 defective pixels in your computer monitor, okay? And then we list their probabilities here, okay? So if I want to find the mean of this situation here, well, looking at the formula, it says, take all the x values and multiply them by the probabilities. Well, that means I just have to take all the x values and multiply them together. So 0 times 0.2 is 0. And 1 times 0.5 is 0.5. And then multiplying down, we get 2 times 0.2 is 0.4. And 3 times 0.1 is 0.3. Okay, so essentially what I'm doing when I find the mean is we're just multiplying down each of the columns. Okay, after we do this, it says, now we have to take the sum. So the next step is to do this. Take my numbers that I just got and add them together. That's all you have to do. And if you do this, you should get 1.2, and that's your mean. Okay. So when you're finding the mean, you can either like remember how to use the formula. If you're good with formulas, just go ahead and do that. The other option is just remember, multiply down the columns and then add up the results. That's all you have to do to find the mean. Okay. Remember, the symbol for this mean is mu x. Any questions about example 3? Nice. Okay. If we flip to the page, I'm going to talk about something the textbook finds really important for some reason. I don't really find it important, mainly because I'm not a business person. In many business applications where you're dealing with money, sometimes you'll see this thing called the expected value. Okay. Whenever you see this, the notation for this is big E and then X in brackets. Okay, we read this as the expected value. And what the expected value is literally the mean. Okay, so the expected value is the same thing as saying the mean or mu x. Okay, they're the same thing. You do the same thing to get it. We just call it a different word, especially when we're dealing with like a word problem, something dealing with money. Sometimes instead of saying the mean is this, they say we expect this. Okay, let's do an example. Here we have a mineral economist. Cool job. And what this economist is doing is it's predicting like the probability of a $30 million loss, a $20 million profit, and a $40 million profit. Okay. X here, our random variable, is representing the profit or how much money that we're going to make. Okay, and the first thing it tells us to do is to make the probability distribution. So we actually have to make the chart here. Okay, whenever we make a chart, well, X is going to be on one of the rows. The probability of X is going to be on the other row. And we basically have to fill in all the things that can happen and then the probabilities of each of them. Okay. What do you think is going to go in the X row? Yeah, like all the losses and the profits, right? So we have, now I'm a math person, so I don't like writing million. I think that's a little bit redundant, especially if everything's in millions. So instead of saying 30 million, I'm just going to write 30. Okay, instead of saying 20 million, I'm going to write 20. And instead of writing 40 million, I'm going to write 40. Okay. Now, when I wrote this out, I actually made a mistake. Does anyone recognize the mistake? You see it? The loss or a profit, right? One of these numbers has to be negative, right? Because if I have a $30 million loss, that's different than like a $30 million profit, right? So how do you think I'm going to make, well, I already said it, to make the difference between a loss and a profit, whenever we're losing something or whenever we're decreasing something, that means a negative number. Okay, so if it says a loss, negative, if it's profit, it's going to be positive. Okay. Now, filling in the rest of the chart is easy, right? The probability of 30 is 0.4, the probability of 20 is 0.5, and the probability of 40 is 0.1. All right. Any questions on how I made this chart? All right, then what I'm going to have you do is I'm going to want you to calculate the expected value. It's the same thing as we did in the last page. We're just calling it a different word, and we'll come back in a little bit. All right, let's come up to the front here. So basically, all you have to do is find the mean or the expected value. Jordan, you want to take us through this one? Mm-hmm. Perfect, right? So whenever we find the mean, you can, of course, remember the formula, which, I mean, tells you what to do. But what I like to do is just remember, multiply down the columns and then add across. Okay, so we got a $2 million answer, okay? And the last question was like, okay, does this venture expect or represent an expected gain or an expected loss? And I think what Jordan did is he, well, meant gain when he said profit. Basically, what this last question is doing is it's just asking us, is our answer positive or negative? That's literally what this last thing is doing. So is our answer positive or negative? I spelled E-G, okay? And since our answer is positive, then this is a 2 million profit or a 2 million gain. Okay, that's all that question's asking. Okay, any questions on example number 4? All right. So expected value, mean, it's the same thing. All right. Yeah. So I guess we have to start talking about variance and standard deviation. Or whenever we talk about mean, there's always a variance and standard deviation to talk about as well. Okay. Still going in with the population symbols. Okay. Does anyone remember the symbol for population standard deviation? I saw Elizabeth write it. It's basically the circle with the line on top, right? It's lowercase sigma. Okay. Does anyone remember the symbol for variance? It's literally that symbol, but squared, right? And it has that symbol because, well, in order to go from variance to standard deviation, all you need to do is take the square root of that number, right? So these two are very closely related. Okay, now I'm going to give you the formulas for the variance and the standard deviation. They're going to look really crazy, okay? And I promise you, you don't really need to know the formulas if you know how to find the variance, kind of like how we did the mean. But I'll give you the formulas, but just promise don't freak out when you look at them, okay? So if I want to find the variance of a random variable, we're going to use that variance formula, sigma squared. But to talk about probability, we're going to do the same thing that we did with the mean. I'm just going to put a little X at the bottom. Okay, so it's the same symbol, just has an X on the bottom. Here's the formula. Okay, don't freak out. It's big sigma in parentheses x squared times p of x. Okay, in the parentheses minus mu x squared. Okay, there's a lot going on here. I promise it's not as bad as how it looks. Okay, so let's just take a look at what this is saying. We take each of the data values x, and it says we have to square them. Okay, after you do that, we multiply by the probabilities. So it's very similar to that mean formula, except we're squaring x before we multiply. Okay, after that, we take the sum, and then we have to subtract off this weird symbol here. Does anyone remember what mu x stands for? It's just the mean, right? So basically what this last part is doing is it's saying subtract off the mean, but square it. Okay, that's all that's saying. Okay. Now, I promise you, I will have a more streamlined way to talk about finding the variance. If you want to use the formula, I do recommend memorizing this because I won't give it to you. Okay, but I promise you, I'll find a way to be able to tell you how to find the variance without like going through what the formula says, because I do think formulas are confusing in this class. Okay, next, standard deviation. Remember sigma, but we're just going to put an x at the bottom just to say we're talking about probability. Okay, and how do you think we're going to go from variance to standard deviation? Square root, right? So the standard deviation is still the square root of the variance. Okay, and I'll make it easy for you. I'll just put variance if I can spell it correctly. There we go. Or if you want to use the symbols, it's just sigma x squared with the square root on top. Okay. Any questions on these two formulas here? Okay, I know they look scary. I promise you there'll be an easier way to go about doing this without like just reading the formula and being able to figure out what's going on. Okay, but this is where my last class ended up because we did have to do a quiz review. Now I kind of messed up when I made this quiz review. On the quiz review, I asked you to find the variance and the standard deviation. I promise you I will never quiz you on something if we don't cover it in class first. So what we're going to do on Friday, we'll have a very short quiz. We'll only do parts A through C